Welcome to the another exciting episode of Machine Learning Mastery. In today's video, we are diving into the fascinating world of logistic regression, a powerful algorithm that helps us solve classification problems. I am Bhaskar and I am thrilled to be your guide to this journey. So let's buckle up and explore the incredible power of logistic regression. Session 1: Understanding Logistic Regression. Before we delve into the magic of logistic regression, let's start by understanding what it actually is. Logistic regression is a machine learning algorithm that aims to predict the categorical outputs. Unlike its cousin, linear regression, which focuses on continuous predictions, logistic regression is perfect for solving the classification problems. One of the key players in logistic regression is the logistic function, also known as Sigmoid function. This is an incredible mathematical tool that maps the output of a linear regression to probability. So let's take an example. We know that linear regression equation is y equal to m1 x1 plus m2 x2 plus so on plus c. Okay, so this is the equation of linear regression. So how can we calculate the logistic regression? How can we create the logistic regression from it? So the logistic regression is nothing but log of odds. That is log of y by 1 minus y equal to m1 x1 plus m2 x2 plus so on plus c. Okay, so let's take log to other side. It will become y minus 1 by y equal to e power exponential m1 x1 plus so on plus c. Okay, so let's take 1 minus 5 to other side. It will be e power mx sigma mx into 1 minus y. So after taking this left side and solving the equation, we will get y equal to e power m1 x1 plus m2 x2 plus so on by 1 plus e power, sorry, it will be minus, okay, and it will be e power m1 x1 plus so on. This will be e power minus. Okay, so e power minus x, e power minus mx by 1 plus e power minus mx. This will be our y. This is our probability. So this is our probability. This is how we calculate the y. So let's learn more about the probability. It allows us to estimate the likelihood of your observation belonging to a specific class. That is, how likely a observation belongs to a specific class. Logistic regression is used for binary class classification. What is binary class classification? It has two values, either 0 or 1. That is the binary class. It can be either 0 or 1. Okay. So to make the sense of probability output, we use decision boundary, a threshold that separates different classes. So let's take an example. If you have a plot, these are your points, and there is one. It's a binary class problem. So x is 1 point, so it's zeros or O's or other points. So if we plot a plot, this is a decision boundary. Okay, this line is a decision boundary. So this boundary helps us to classify new observations based upon the predicting probabilities. It's like drawing a line in the sand, telling us which side an observation falls into. The beauty of logistic regression extends beyond the realm of machine learning. It finds its applications in diverse domains such as finance, healthcare, even social sciences. From sentiment analysis to fraud detection and medical diagnosis, logistic regression is a versatile tool that empowers us to make informed decisions based upon categorical outputs. So let's move on to the section 2, logistic regression model and its applications. Okay, so let's take a closer look at the inner working of the logistic regression model itself. At the heart of logistic regression lies the logistic function and logots. That's nothing but Logit transformation. These mathematical elements allow us to estimate the probability of your observation belonging to a specific class. By analyzing the coefficients, we gain valuable insights into the importance and impact of different features on our classification models. Let's take an example. All right. So we have a logistic regression log of y by 1 minus y equal to m1 x1 plus em2 x2 plus so on plus bias term. This is our log of odds. You can see, right, m1, m2 and so on. m1, m2, so on, m3, m4, m5, so on up to mn. These are our coefficients. These are our coefficients of our logistic regression. So this also act as an variables of importance. That means the coefficients define the importance of a particular variable in the model. Okay. So what do you mean by it? X1, X2, X3, X2, X3, so on up to Xn. These are our variables. M1, M2, so on M1. These are our coefficients. So the importance of a variable is defined by the coefficients. That means if x1 equal to 0.9, x2 equal to 0.8, x3 equal to 0.7. So what is the order of importance of variables? It's simply x1 greater than x2 greater than x3. That is, x1 variable is more important for the model. That means x1 variable has major impact. It is the most important feature that helps us predict the y. Okay, if you see x3, x3 is the least important feature in our model. So based upon this, we can do variable selection. Okay, but wait, there's more. Feature selection and regularization techniques plays a crucial role in improving the performance of our logistic regression model. They help us select the most relevant features and prevent overfitting, ensuring our model generalizability. We select the features to prevent overfitting. So we can also use regularization. We can use two kinds of regularization here, N1 regularization and L2 regularization. So what's the difference between N1 and L2 regularization? Let's find it out. So if you see our model, so it will be log of y by 1 minus y, the or probability. Okay, it will be our equation m1 x1 plus m2 x2 plus so on plus c, a constant. So how can we regularize this? If we add L2 regularization, it's nothing but sum of its coefficients. That's it. This makes us our model L2 regularize. I mean square. This makes us our model L2 regularize. What about L1 regularization? This is for L2 regularized. What about L1? So let's again take our equation log of y by 1 minus y equal to m1 x1 plus m2 x2 plus so on plus constant. How to make it L1 regularize? We can simply make it L1 regularize by adding the sum of coefficients, just a sum of coefficients. So L1 means adding sum of coefficient values, and L2 means adding sum of squares of coefficients. Okay, this makes our model L2 regress. That means logistic regression is L2 regress. Next, handling categorical and numerical features is another essential aspect of logistic regression. For categorical features, we convert them into numbers. Yes, computers only understand the numbers and our models work only with numbers. Remember, in machine learning, AI, data science, deep learning, and any model, everything works in numbers. So if you have category feature, what will you do? Convert them into numbers. Got it? Yes. Let's move on to the next session, evaluation and assumptions. Now that we built our logistic regression model, it's time to evaluate its performance and explore its assumptions. We will dive into the techniques like cross-validation and ROC curves to assess the performance of our logistic regression model thoroughly. These methods help us measure how well our model predicts the true classes and make informed decisions based on its performance. Cross-validation is an approach to improve the metrics. Okay, one popular approach of cross-validation is k-fold cross-validation. So let's get into details. K-fold cross-validation. Split the train data into k folds. That means this is our train data. So this is our train data. We split it into k folds. That means k equal parts. So 1, 2, 3, so on to k. So what will you do? We divide into, for each step, we keep one fold aside and k minus 1 holds as our train data. So this will be our train for one iteration, and this will be our test or validation data. Okay, so we'll be training on the train data and we'll be testing on the validation data. We get our metrics. What will we do for second iteration? The second iteration, assume this is a k folds. The first iteration we have taken this. Okay, so in second iteration, what we will do is we will be taking this part, and so our train will be this part plus this part, and this will be our validation or test data. So now also we have k minus 1 holds for train and one fold for validation. And we'll train a model like this. We will train it for how many times? K times. That's why it's called K fold cross validation. Okay. For each time we will get output the metrics on one fold, and we connect it for K times and we will get metrics or K folds. This is how we conserve our data. We are not wasting our data because of the train and test split. So by using this method, our model will be more robust. Now that we understand about the K-fold, let's go to other topic. Receiver operating characteristic curve, also called as ROC curve in logistic regression. So it helps us to understand how well the model can distinguish between two classes. To explain ROC in simple terms, imagine you have a logistic regression model that predicts whether a email is spam or not. The ROC curve visualizes the trade-off between the model's true positive rate, also called as sensitivity, and its false positive rate, or 1 minus specificity. So what is true positive? So these are the instances where our model correctly predicts the positive class. So in our example, what it will be? So number of instances which the model correctly identifies as spam emails. That's our true positive. False positive. These are instances where model incorrectly predicts the positive class when actual class is negative. That means it wrongly identifies non-spam emails as spam. We are falsely predicting as positive. True negative, we are truly predicting as negative. That means correctly identifying non-spam emails. They are negative. So we truly predicting as negative. That's true negative. False negative. We are falsely predicting them as spam. But in actual, they are not spam. That's the false negative. To create the ROC curve, the model predictions are sorted based upon their probability scores and threshold is applied to determine whether each instance is classified as positive or negative. So, if we have a probabilities, let's take example. The probabilities are 0, 0.1, 0.2, 0.3, and so on. Let's take it's a line, linear line. Okay, so for one time we will take a threshold as here. Let's take it as here threshold. This is our probability threshold. So whatever is the negative, whatever is the left side, we classify it as negative. Whatever is the right side, we classify it as positive. So, and by doing that, we calculate our true positive, true negative, false positive, and false negative. Okay, this is one step. For the second step, what will you do? Same line 0.1, 0.2, 0.3, and so on. This time we take threshold here. This will be our threshold, and whatever is the left side, it will be negative, and whatever is the right side, it will be positive. Again, similarly, we'll calculate true positive, true negative, false negative, all this stuff, and we will get our matrix. So let's go on. So by adjusting this threshold, we can control the model's sensitivity and specificity. The ROC curve is generated by plotting the true positive rate on y-axis and false positive rate on x-axis. That means y-axis we will be having true positive rate PPR, and on x-axis we're having false positive rate. If you plot this, it will give you a ROC curve. This is your operating characteristic curve. What if our plot is y equal to x? That means it splits the both x-axis or y-axis equally. It signifies it's a random model. So there is one more concept here, AUC, area under ROC curve. So how will the curve look like? The curves will be like this. This is one plot. This is one plot, like that. So we got a random model. Then what is a perfect model? Predictions are 100% accurate. It's simply this point, this line. If it is true positive rate and false positive rate, this line. This will be a perfect model. This will be our random model. And generally our models will lie between perfect model and random model. This will be our model. So the more the plot moves towards y-axis, the better the model it is. Right? Let me repeat again. The more the model moves towards the y-axis, the better the model it is. Then what is AUC? It is simply the area on the curve. Just plot this area. This will be our AUC, area under plot, area under the curve. Okay. So now that we understand AUC, let's move further. A perfect classifier, as I said, it will be TPR equal to 1 and FPR equal to 0, indicating high sensitivity and low false positive rate. The area under curve is calculated, which quantifies the overall performance of the model. Here AUC of 1 indicates perfect classifier, while AUC of 0.5 suggests a random guess. So in summary, the AUC curve in the logistic regression helps us assess how well the model can distinguish between positive and negative classes by visualizing the trade-off between positive, true positive rate and false positive rate. It provides a useful tool to evaluate and compare different models in binary classification tasks. From sentiment analysis to fraud detection, medical diagnosis, logistic regression is used. However, it's essential to understand the limitations and assumptions of the logistic regression. There may be instances where alternative algorithms might be better suited for your classification problem. By understanding these limitations, you will be better equipped to make informed decisions when choosing your machine learning approach. Assumptions in logistic regression are certain conditions that needs to be satisfied for a model to be valid and provide accurate predictions. Here are the assumptions of logistic regression explained in simple terms. Number one, binary outcome. Logistic regression assumes that outcome variable you are trying to predict has only two possible outcomes or classes. For example, it can be either 0 or 1. That means it can be either a spam or not spam. Or it can also be either a customer will churn out or will not churn. Or whether a patient has settled disease or is not having. It's a binary outcome, only two outcomes. That's our binary outcome, assumption number one. Assumption number two, independence of observations. The observations or data points used in logistic regression should be independent of each other. This means the outcome of one observation should not be influenced by or related to the outcome of other observation. Each observation should be treated as separate and unrelated data points. The second example, if we plot a plot between the data points like this, if you plot a plot between data points, these are data points, right? So this data point should be independent of this data point. So that means our y1 and y2, two data points, two equations. Y1 should be independent of y2. Let's go to next assumptions. Linearity of the logit. Logistic regression assumes that relationship between the predictor variables and log of odds, that's logit of outcome is linear. That means in our plot y by 1 minus y of log of this one should be in linear relationship between our independent variables. So this equation of a line, this is our probability. This is in linear relationship between our variables, independent variables, right? So that's our assumption, linearity of log it. Next assumption, low multicollinearity. That means x1, x2, x3, these variables should not be dependent on each other. They should be independent. So, yes, I have taken in the last video, in my linear regression example, let me repeat it one more time. Let's take x1, x2. x1, 1, 2, 3, 4. x2, 2, 4, 6, 8. Is x1 and x2 all dependent on each other? Is multicollinearity violated here? Yes. How come we know? x2 equal to 2x1. So multicollinearity is violated because x1 and x2 are dependent on each other. So we should not have this kind of dependency. What will we do if we have this kind of dependency? Well, remove all variable. That's all you need to do. Let's take next assumption. Large sample size. Logistic regression assumes that you have sufficiently large sample size. While there is no fixed rule for what constitutes a large sample size, having a larger sample size generally leads to more reliable and stable estimates. So, what do we mean? That means these data points should be large enough. That's all. That means we should have more rows. Important point to note in data science is your rows should be greater than your columns. That means number of rows should be greater than number of columns. This is not good. This is better. These assumptions help ensure that logistic regression models are reliable and provide accurate predictions. It's important to assess and validate these assumptions before relying on modern predictions. So, and remember, logistic regression isn't limited to binary classification problem. That means we can do multi-class classification problems with logistic regression. How can we do? We can employ a few techniques like one versus rest or one versus one. So what are those? Let's take an example. Let's take one, two, three, four, five. These are the categories. One category and the model of our one more category, one versus one. So taking only one category, one model, second category as one model. Similarly, taking one category as one model and other category as one model. So we are trying to compare. That means whether our model is 3 or 4. Similarly, whether our model is predicting 1 or 2. Like this, we will build n into n minus 1 by 2 models, and whichever is having the highest number of predictions. That means, for example, 3 is occurring most of the times, then our final prediction will be 3. This is 1 versus 1. 1 versus all or 1 versus the rest. That means it can be either 1 for 2, 3, 4, 5 categories. It will be n, not 1 on n. And similarly, for 2, we will be predicting, we will be building a model. It will be 1, 3, 4, 5. It should be either 2 or not 2. So we will build n models. Here we will be building n models, and whichever is the highest probability, that will be our classification. So that is one versus all, one versus the rest. Okay, remember, loss regression is not limited to binary classification. That means, as I said, as we have discussed, we are using for multi-class classifications also. Congratulations! Now you have gained a solid understanding of loss regression for classification problems. I encourage you to apply this newfound knowledge to your own projects and continue exploring the exciting world of machine learning. If you want to deep dive into the other advanced algorithms and techniques, make sure to check out the other videos in our machine learning mastery playlist. Remember to like, subscribe, and share this video to support our channel and help us bring more exciting content. Thank you so much for joining me today. I appreciate your time and enthusiasm in learning about logistic regression. Keep pushing the boundaries of your machine learning journey, and I will see you in the next video. Happy learning. Thank you.